So what we're going to do this time is we're going to do another lecture series based on the fact that we have this coronavirus scare at the universities. So lectures have been canceled for a couple of days, possibly a couple of weeks. What I'm going to do is post a bunch of these lecture series free on YouTube so that we can keep the lecture train going. Last time what I did was I did matrix multiplication, and then I showed why we're going to want this matrix multiplication to solve linear systems. This time what I'm going to do is define a few more things, and then we're going to continue on our way to finding what we mean, a bunch of the algebraic and arithmetic tools that I need to compute the inverse of a matrix so we can solve linear systems. Definition: let A be an m by n matrix. The transpose of A, denoted A capital T, it's not an exponent, it's the transpose, is the n by m matrix obtained from A by making rows of A columns of A transpose and vice versa, making the columns of A rows of A transpose. So we're interchanging the role of rows and columns of A transpose. As an example, let A equal 1, 2, 0, 3, negative 1, 4, which is a 3 by 2 matrix. If I want to transpose this, what do I want to do? A transpose is going to be the 2 by 3 matrix with 2 rows and 3 columns. How do I get this? I take the rows of A and make them columns of A transpose. So the first row is 1, 2, so I make that the column 1, 2. The second row is 0, 3, so I make that the second column of A transpose, and 1, 4 becomes negative 1, 4 is this column. This is transpose. One other thing we may need, so I'll sneak it in right now, is the trace of a matrix, but the matrix this time can't be any arbitrary matrix. Oh, there goes the cap. It has to be a square matrix. So let A n by n be a square matrix. The trace of A, denoted by TR of A. So the trace is the sum of the diagonal entries AII of A. What does that mean? The trace of A is equal to A11 plus A22 plus dot 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 plus ANN. Remember, A is going to look like this: A11, A12 dot 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 A1N, A21, A22, A2N dot 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 AN1, AN2 dot 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 ANN. So if it's square and n by n, what that's saying is you're going to take just the diagonal entries and add them. And that's what the trace of a matrix is. Not hard to compute, but extremely useful later on in linear algebra. This is the trace of a matrix. As an example, here's one baby example. I have these two matrices, A and B. A is 2 by 2 and B is 3 by 3, so they are both square, so the trace is defined. If I want the trace of A, this is equal to A11 plus A22, the sum of the diagonal entries, which in this case is 2 plus 7, which is 9. The trace of B is equal to A11 plus A22 plus A33, the sum of the diagonal entries, which is going to be this time 14, which is 1 plus 5 plus 9, which is 14. Trace of a matrix is the sum of the diagonal entries of that square matrix. The next two definitions we use, one of them we always create when we create REF of an augmented system anyways, and they are extremely useful in the properties or computing determinants and other things later on. So we're going to define upper triangular and lower triangular matrices. A matrix A n by n, so a square matrix, is called lower triangular if all entries Aij are 0 above the main diagonal, i.e. if A looks like this. So what are they saying? Upper triangular. I'm going to draw it for you so you can see. They're saying if all the entries are 0 above the main diagonal, we call this a lower triangular matrix. It seemed reverse at first. So what we're saying is A is going to look like this: A11, A22, dot, 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 ANN. And then we're going to have A21. These are going to be non-zero. And then we're going to have AN1, AN2, dot, dot, dot. But up here, we're going to have zeros. So we get zeros above the main diagonal. There's zeros everywhere. 0 everywhere. And so what we're saying with that is, this is why we call it lower triangular, because now we have a triangle of information. All the information in this matrix is essentially in the lower triangle, as we have zeros above. So if this is the case, we say that, and what is that going to say? We say that Aij is 0 if what? If the indices, this is A12. So if I is strictly less than j, because the 1 is less than the 2, all of those guys are 0. This is also what they would say for lower triangular. All the information is in the lower triangle. All the above the main diagonal are zeros. We're going to flip that right on its head and discuss upper triangular. So magic. An n by n matrix is called upper triangular. If all entries Aij are 0 below the main diagonal. So what does that mean for us? A equals A11, A22, dot, 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 ANN again. But now these are non-zero. A12, we don't know. A1n, and then dot, 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 A2n, dot, dot, dot. This is now what we have, an upper triangular, and then we have zeros below, 0, 0, 0, zeros everywhere. So now we're calling it upper triangular if the information is in the upper triangle and we have zeros below the main diagonal. We say we're upper triangular. There's my triangular. Upper triangular if Aij is 0. If we have now what happens if I is larger than j, is another horrible way of saying it. Essentially, this is what they're saying for upper triangular and lower triangular. An n by n matrix is called diagonal if it has zeros everywhere off the main diagonal. And you can show that A is diagonal if and only if it's upper triangular and lower triangular. These are also useful matrices later on in theory, so we want diagonal matrices. So what is that going to look like? D diagonal. If it looks like a diagonal, what we're going to say is, some books will use the terminology dag, D-I-I. And what that means is, because we know we have zeros everywhere except for on the diagonal where the indices are the same, what they're saying is we would have this D11, D22, to DNN, and then zeros everywhere else. So this is a diagonal matrix. Coincidentally, some of these can be zeros. It didn't say anything about those being zeros on the diagonal. All they said was you have to have zeros off of the main diagonal, everywhere not on the main diagonal. So, and this is the notation they use to just say that I entry will be these entries for diagonal matrices. All right, as an example, let's look at a few of these matrices and decide whether they're upper triangular, lower triangular, both, or neither. So is the first matrix upper triangular or lower triangular? So to be upper triangular, I want this kind of scenario where I have information in the upper triangular, and to be upper triangular, I have to have zeros below the main diagonal, which I do have. So this is upper triangular, but not lower triangular, because to be lower, it would have to have a zero above the main diagonal, and we don't have this. For the next matrix, if I look at this, to be lower triangular, I would have to have this to be non-zero, or I have to have at least, what do I have to be lower triangular? I have to have zeros above the main diagonal, which I do. So it didn't say anything about having zeros on the off diagonal. I don't care about this, so this is lower triangular and not upper. This matrix has zeros on the diagonal, but has both off diagonals non-zero, so this is not upper triangular, and this is not lower triangular either. It's neither upper or nor lower triangular. The zero matrix for 2x2 has zeros on its diagonals, but it definitely has zeros on the off diagonals also, so it is both upper triangular and lower triangular. And therefore is diagonal. One more matrix, if we talk about D being 1, 0, 0, 2, this is a diagonal matrix. D1, 1 is 1, and D2, 2 was 2, and we have zeros off, so D is a diagonal matrix, which means it is both upper triangular and lower triangular. So this is what we're talking about with upper triangular matrices, lower triangular matrices, and diagonal matrices. Since I've done that, and as we're going to build the algebra for matrix, the set of all matrices, m by n matrices, we might as well give one more definition of, once we've added and multiplied and those types of things, we definitely want for every size the zero matrix. So let's give that now. Definition. The zero matrix of size m by n is the m by n matrix with all zero entries. So 0 is going to be 0 dot 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 0, 0 dot 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 0. For every size there is a zero matrix. Coincidentally, what do we know about the zero matrix? What's going to happen with that? 0 plus a equals a, which equals a plus 0 for every matrix. So this is the guy that leaves everybody alone when you add matrices, the zero matrix. Now that we have most of the arithmetic, or the arithmetic that we need to define these things, we're going to show that in fact the set of all m by n matrices is in fact a vector space on its own. You can skip forward if you don't want to see this again, but basically I'm going to quickly show you all 10 axioms for the vector space matrices now. Let's consider the set m by n r of all matrices of size m by n. Let's consider matrix addition and the zero matrix, and then let's talk about scalar multiplication and the scalar 1. This is a vector space, i.e. what do we mean by vector space again? It's got 10 axioms. Let's quickly go through them and give them a name, possibly out loud at least. 1, when you add two matrices, you don't create anything new, so we have closure of matrix addition. If they're the same size, it's defined and it creates a matrix of the same size m by n again. So this is in m by n r. It's in that set again. Closure. 2, when I add two matrices, it doesn't matter which order I do this in. Matrix addition is commutative. 3, if I add 3 of these things, it doesn't matter whether I start at the front or the back. We have associativity of addition for matrices. 4, we just introduced this. There's a 0 in m by n r such that what? 0 plus A equals A for every matrix. And then the clouds have to shift. The weather's changing. 5 for the better, hopefully. Once we have this, there's a, for A in M by N R, this implies there is negative A in M by N R, such that what? A plus negative A equals the 0 matrix. There's negatives. Who is negative A? Scalar multiplication says you put negative onto every entry, and that's who the guy is. 6. When I scalar multiply matrices, I don't create anything new. So K times A is in M N by N R again. Closure of scalar multiplication. You don't create anything new. You create this new matrix, which has M rows and N columns still. 7. If I take 2 scalars and multiply it by A, I can associate and write that as K times L times A. Move all the numbers to the front when you do this. Scalar associativity. 8 and 9 deal with 1 scalar and 2 matrices distribution, or 2 scalars and 1 matrix. You can distribute a scalar onto 2 matrices. It is K times A plus K times B. And then if I have L plus K and a matrix, I can distribute the matrix onto that scalar multiplication. That's L times A plus K times A. And 10 is we have a 1 in R is such that 1 times A is A. We have scalar identity. These 10 axioms say that the set of all M by N matrices with matrix addition, the 0 matrix, scalar multiplication, and the number 1 R in vector space over R also. And they give us a whole bunch of the algebra that you're now allowed to use. Because we now have a matrix multiplication, a true matrix multiplication, plus transpose and a few other things, we're going to be able to use those things to create more algebra and talk about a true multiplication and look at some of the properties of matrix multiplication and identity matrix and inverse of matrices multiplicatively. Let's do that next. Let's do some matrix multiplication arithmetic. Basically, what they're saying here is a few more things that we have. Because we have a true matrix multiplication, we want to see the few other properties that we are actually allowed to do with matrix multiplication and matrix addition. The 3 that we're going to do is we're going to let A, B, C now be square matrices in M N by N R. I don't want to talk about, in the more general theorem, we need that to do matrix multiplication, they have to be in the appropriate spaces so that we can do this mixture. But we're just going to pretend that they're all square matrices. So matrix multiplication is defined in both directions, but they may not be commutative. If I have A, B, C, which are for simplicity square matrices, so that matrix multiplication is defined in each scenario where it's relevant, then we have 1 A matrix multiplication, B plus C is A matrix multiplication, B plus A matrix multiplication, C. Matrix multiplication distributes onto addition from the left. This is left distribution. We also have right distribution. 2, if I have B plus C and I matrix multiply on the right instead, you can distribute this through, and this will be B matrix multiplication A plus C matrix multiplication A. Notice that I can't just flip those around because we do not have the property of commutativity of matrices. In the previous video, we showed that A times B can be defined where B times A in general may not even be defined. So A times B definitely does not equal B times A. A times B does not equal B times A. That should be listed, but we usually don't list that. But for you, that's a thing. Don't just flip them around. And then 3, we can actually associate matrices too. So A matrix multiplication B times C is the same thing as A times B matrix multiplication C. So you can associate the brackets. So these are the extra properties we need for matrix multiplication. Now what we're going to do is we're going to start trying to define somebody who plays the same role as 1 times A. When we do that for numbers, 1 is the guy that leaves everybody alone. Now what we want is somebody we're going to call IN times a matrix, which is going to leave the matrix alone. So who is that guy? our next definition. Why are we trying to do that? Again, now that we have true matrix multiplication, I want to be able to use all this algebra and clever rules to solve linear systems by multiplying by the inverse matrix. First, I need an identity matrix, and then I need the inverse multiplicity of A, called A minus 1, or the inverse of A, and we need to build that machinery. So doing that story, to find the inverse of a matrix, first we need the identity matrix. So we'll do that next. Definition. The n by n identity matrix, so it's square, In, we don't have to write n by n because it's going to be in dimension n every time it's square, is the matrix with ones on the main diagonal and zeros elsewhere. I.e., the n by n identity matrix looks like this. I have 1, 0, 0, dot, 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 zeros. 1 and A1, 1 is 0, and then 0, 1, 0, dot, 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 0, and then 0, 0, 1, dot, 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 0. Ones on the main diagonal is what it's saying, and then zeros elsewhere. This is the main diagonal, and so this is the identity matrix. What do we want to have happen with that? Which is exactly what the next theorem is going to say. If I multiply this matrix by any other n by n matrix, I'm going to get that it leaves the matrix alone. Before we do that, just so that you can see, we have one in every dimension. When n is 1, I1 is the 1 by 1 matrix, this, which is the number 1, and we know that 1 times A equals A for any real number A. So in one dimension, the 1 by 1 identity matrix is the number 1. When n equals 2, we have I2, which is 1, 1, 0, 0. Notice that it is both upper and lower triangular, or a diagonal matrix, so the identity matrix is always a diagonal matrix. So this says that I2 times any 2 by 2 matrix is going to be, they're going to claim is going to be a 2 by 2 matrix. Let's just do that, and then we'll state the theorem in general. So, but for 2 by 2, can you see that? Why is that? I2 times A. Well, what does A equal? Let's call it A, B, C, D, like we always did. That's going to give us 1, 0, 0, 1 times A, B, C, D. What are we going to get? This is 2 by 2 and 2 by 2, so the inside indices match, and the size will be the same, 2 by 2. What are we going to get? We're going to get 1 times A plus 0, so A, and then we're going to get 1 times B plus 0, which is B, and then we're going to get 0 and then C, and then 0 plus D, which is D, which is A. This means that I2 times A gave me A again for any 2 by 2 matrix. This is exactly what we want before we state the theorem for n equals 3, just so you can see it. This is usually where you're going to work, is in 2 and 3 land, possibly 4 or 5, but at first when you compute it's 2 by 2 and 3 by 3 matrices. So 1, 0, 0, 0, 1, 0, 0, 0, 1 is the 3 by 3 identity matrix. When I use matrix multiplication, you can see that this is the guy that's going to leave everybody alone when we do matrix multiplication. And that's exactly what the theorem is going to say. Theorem. Let A be an n by n matrix and In be identity. Then In times A equals A, which equals AIN. This is the result that we want. And I showed it for 2 by 2. This does indeed work. We have to show both statements coincidentally because we don't know that matrices commute, so I don't know that I times A is equal to A times I, but in this case it is in both scenarios. Alright, so now that we have the identity matrix, one quick application I'm going to squeeze in there is we have a theorem which tells us when we row reduce a matrix or use Gaussian Jordan elimination to go all the way to RREF, or row reduced echelon form, there's only 2 cases. We either can create the identity matrix or we have at least one row of zeros. So let's say that theorem. let A be an n by n matrix then its RREF, or reduced row echelon form, is either the identity matrix by n or the reduced row echelon form has at least one zero row. What they're saying with this essentially is this: if I have A, which is n by n, then I can use magic Gaussian Jordan elimination to go all the way to RREF. In that RREF, I either can turn A into the identity matrix IN, or in that reduced row echelon form, I have at least one row of zeros, is what it's saying. So every matrix can be augmented using Gaussian Jordan elimination into either the identity matrix or a matrix which has at least one row of zeros. We're finally now at the stage and we have all of the pieces that we need to define what the inverse, multiplicative inverse of a n by n matrix is. So what we'll do first is we'll give the definition, the generic definition of what an inverse is for an n by n matrix, and then we should always be asking ourselves the more important question of, given an n by n matrix, how do I find the inverse, and how do I tell even if it has one, first of all? And then if I have a decision-making process which tells me whether it has one, how the heck are we going to find these things? Definition. Let A n by n be a square matrix. A matrix B is called an inverse of A if A times B is IN, which is B times A. So if when I matrix multiply these things together, I get the identity matrix. Oh, we're going to get the rare visit from Noodles the cat. Noodles likes to do some math too, so he's going to hang out with me for a second. He wanted to see what was going on. So this is the definition of an inverse of a matrix. In such a case, what we do is, I know that's pretty exciting out there. I want to do some math. We're doing matrices. Yeah, inverse matrix. This one's Noodles. This is the male cat. He's all black. Halloween cat. So if I do have an inverse, in such a case, we write B is equal to A minus 1. So the inverse is the notation we're going to use. And say that A is invertible or non-singular. So this is our definition of the inverse of a matrix. If there is another matrix that we can multiply it by, which will give us the identity, this is the inverse of a matrix A. Okay, you go see what's going on. Go see. All right, now that we have the definition of inverse, what we're going to ask ourselves is correctly, how the heck do I find it given a matrix A? And how do I tell if it even has one? Do they always exist? What's going on? What we're going to do is do the 2x2 case, and then in the next video, in the next lecture, we're going to show you that we'll give you a condition on, we're going to give you two methods essentially in the next lecture. The first method is going to use row reduction and Gaussian elimination to find the inverse of a matrix. And at first that'll be all right because you don't need any new machinery or clever definitions or anything, and you already know how to use Gaussian Jordan elimination to get to RREF fairly efficiently, so you're like, I like this. What's wrong with it? Fractions abound, and the computations to do large matrices and row reduce all the way to RREF, and using the clever trick that we're going to use, this can become computationally daunting. Lots of fractions. The other way we're going to show you is we're actually going to have an algebraic formula for it, and it's going to be 1 over the determinant times there's a joint which has all the cofactors transposed and all this, and you're like, now I'm going to have to remember determinant calculating and cofactors and transpose and all this. Why would I ever do this? Well, the fractions won't appear, or the computations become much simpler once I have a handle on all this machinery. This computation using the formula will not introduce fractions until the end, so I won't have to do all this row reduction fraction business. So we're going to give you 2 methods for computing inverses. They both have positives and negatives, but let's go through them. First of all, let's do the 2 by 2 case for 2 by 2 matrices. How do we find the inverse? For the 2 by 2 case, let A equal A, B, C, D. Then what we're looking for is the inverse B. Suppose we're going to call it B, and we're going to call it x1, x2, x3, x4 cleverly, so that you can see those are the unknowns that I'm going to look for. And who is the identity? I2 is 1, 0, 0, 1. And by definition, just using the definition, and then we can algebraically cleverly solve for this. Like I was saying in the previous lecture, in the very second definition we give, we state when 2 matrices are equal to each other, and we say matrix A is equal to matrix B if all the corresponding entries are equal. We're now going to use that clever property. What does the definition of these being inverses say? That says A times B equals I2. But now we have actual expressions for these things, so that's going to be A, B, C, D, matrix multiplication times x1, x2, x3, x4 is equal to 1, 0, 0, 1. These 2 matrices now have to be equal. But before we check that condition, let's actually do the matrix multiplication. This is 2 by 2. This is 2 by 2. And so the outcome should also be a 2 by 2 matrix. And that will give me 2 rows and 2 columns. And that has to equal 1, 0, 0, 1. What do I get there? This is A times x1 plus B times x3. AX1 plus BX3. And then AX2 plus BX4. In the second row, it's CX1 plus DX3. And CX2 plus DX4. And now we're asking the first thing we asked in that previous lecture. When are 2 matrices equal? This matrix has to equal this matrix, and if and only if the corresponding entries are equal. So this has to equal this one has to equal this one has to equal this, and these guys have to be equal. So let's write that out as a system of 4 equations and 4 unknowns and try to find x1, x2, x3, x4. That gives us AX1 plus BX3 equals 1. This has to equal this. AX2 plus BX4 has to equal 0. This has to equal this. CX1 plus DX3 equals 0. And this has to equal this. So CX2 plus DX4 has to equal 1. This is a 4 by 4 linear system of equations, which is non-homogeneous. What I want is an augmented matrix first. Let's do that. A0, B0, 1, 0A, 0B, 0, C0, D0, 0, 0C, 0D, 1. Now I have an augmented matrix. What I need is A, B, C, D such that we have a unique solution is what I'm looking for to this system. And we're looking for x1, x2, x3, x4. So this wasn't entirely a tail-chasing exercise when we tried to make you find A or A and B such that this system has a unique solution, no solution, infinitely many. Now what we're asking to find the 2 by 2 inverse of a matrix, we want to solve this system and we want A, B, C, D to be such that we have a unique solution for x1, x2, x3, x4. And what is the condition? You have some time, you have no lectures right now for the next few days. Try to calculate and find, row reduce this and find the conditions. I'm going to give you them in the theorem that we're about to state, I'm going to summarize all the things we just did and sketch the proof of that. But the idea is, if you can find the conditions and find these unique A, B, C, D such that we have a unique solution, you find exactly when we have an inverse. What is that? The next result. Theorem. Let A equal A, B, C, D be a 2 by 2 matrix. Then A minus 1 exists. So A is invertible if and only if the determinant of A, which is AD minus BC, is not 0. And in such a case, the inverse of A is equal to 1 over the determinant of A, which is AD minus BC. That's why it has to be non-zero for it to exist. We're going to divide by it. And then D, A, negative B, negative C. Also, at first, remember this is a number and we're scalar multiplying. So the real inverse is D over AD minus BC. Negative B over AD minus BC. Negative C over AD minus BC. And A over AD minus BC. This is the x1, x2, x3, x4 that we were looking for. That's the unique solution to that system. It happens if and only if AD minus BC is not 0. For you at first, what are you going to do? For 2 by 2 matrices, you now have a clever formula which you can memorize or practice a whole bunch and compute the inverse of a 2 by 2 matrix. Let's do one example of that and then we'll finish this lecture off. Example. Let A equal 2, 3, 5, 7. Determine if A is invertible, and if it is, find its inverse A minus 1. Solution. A is a 2, 3, 5, 7. So the determinant of A is 2 times 7 minus 5 times 3, which is 14 minus 15, which is negative 1, which is not 0. The determinant is not 0. This says that A minus 1 exists. Moreover, the theorem tells me that A minus 1 is 1 over the determinant, which is minus 1, times you flip the main diagonals, 7 and 2, and you put negatives on the off diagonal, negative 3, negative 5. This is the inverse of the matrix. You coming back for more? So this is the inverse of a matrix. This is Noodles, the all-black male cat who runs the show. Please subscribe below, and if this is for your lectures specifically, I will do another one of these. We will continue by doing the inverse of any n by n matrix and then show how to use these things to solve linear systems. And before we do that, we're going to need the machinery of determinant of an n by n matrix and cofactor expansion. Please subscribe below, hit the bell for notifications for the further lectures. This is Noodles. I'm the Tutor Wizard. I'll see you next time.